We trust symmetry. Every bird, every insect, every airplane since the Wright brothers balanced, mirrored, predictable. It feels natural, safe, but what if nature isn't optimized for Mach 1? What if, for the last 70 years, we've been flying the wrong shape? It is 1955, Langley Research Center, Virginia. Inside a wind tunnel, a strange model is mounted on a central pivot. It looks broken, like someone twisted one wing forward and the other back. No serious aircraft should look like this. No fighter pilot would trust it, and yet the data says it works. The man behind it is Robert T. Jones, already one of NES's most brilliant aerodynamicists. His earlier work on delta wings transformed supersonic aircraft design, but now he's pushing something far more radical. An airplane that abandons symmetry entirely. To understand why, you have to go back to the moment humanity first slammed into the so-called sound barrier. By 1920, the fastest aircraft barely touched 300 kilometers per hour. By the 1940s, speeds had tripled. Then progress stalled. Pilots reported violent buffeting near Mach 1. Controls froze, wings failed. Aircraft disintegrated midair. The sound barrier seemed real, until 1947, when Chuck Yeager flew the bell zone past Mach 1 and shattered the myth. The barrier wasn't a wall, it was a regime change. Supersonic flight obeyed different aerodynamic rules. Engineers adapted quickly, swept wings, thin airfoils, delta shapes, but a new problem emerged, one that still haunts aircraft design today. An airplane optimized for supersonic flight performs poorly at subsonic speeds, and an airplane optimized for subsonic flight suffers massive drag near Mach 1. Long straight wings are efficient at low speeds, great lift, low stall speeds, manageable takeoffs. But they generate crippling wave drag as you approach transonic and supersonic regimes. Thin, sharply swept wings slice through supersonic air, but produce weak lift at low speed. They demand longer runways, more thrust, more fuel. Variable sweep wings tried to solve this, wings that pivot backward in flight. Straight for takeoff, swept for speed. It worked technically, but the pivot mechanisms had to absorb enormous loads. Center-off lift shifts demanded heavier stabilizers. Complexity ballooned, weight increased, cost followed. Only a handful of military aircraft ever used them. None remain in production. The trade-off seemed unavoidable. Until Robert Jones asked a question that made other engineers uncomfortable. Why must the wings sweep symmetrically? Why not rotate the entire wing like a single blade? The oblique wing is deceptively simple. One long wing mounted on a central pivot. Rotate it so one tip sweeps forward and the other sweeps back. From above, it resembles a giant scissor cutting through the air. Intuition screams that it would corkscrew uncontrollably, but air does not care about human intuition. Lift depends on local airflow and pressure distribution, not visual symmetry. Jones' calculations showed something extraordinary. At transonic and supersonic speeds, the asymmetrical arrangement dramatically reduced predicted wave drag compared to a conventional swept wing. In other words, symmetry was costing performance. At lower speeds, the wing could rotate back to a straight configuration, restoring efficient lift. And like variable sweep wings, the oblique design required only one pivot, the loads were simpler, the center of lift shifted minimally. Structurally lighter, mechanically simpler. Secret German documents discovered after World War II hinted that similar ideas had been explored in 1942. But no prototypes were built. Jones pushed forward anyway. By the mid-1970s, NES moved beyond theory. A full-scale, remotely operated test article was developed. Wind tunnel data accumulated. Stability predictions improved. Boeing and Lockheed were asked to study oblique wings for commercial transports. Both concluded the concept could enable faster, more efficient air travel. Timing mattered. By 1975, Concorde, its dream of mass supersonic travel, was already revealing its fatal flaw. Its elegant delta wing was optimized for Mach 2, but at low speeds it produced so little lift that afterburners were required just to take off. Fuel consumption was staggering. When countries banned supersonic overflight due to sonic booms, Concorde's business case collapsed. It could not efficiently cruise subsonic. Boeing's analysis suggested something radical. An oblique wing airliner could cruise at Mach 1, 2 without producing a sonic boom audible on the ground. Transcontinental flights over populated areas could be 50% faster than existing airliners. Takeoff thrust requirements would be lower. Noise reduced, fuel burn decreased, the implications were enormous. NASA decided to stop theorize and began build. In 1976, development began on the Dun, the first piloted oblique aircraft. It was modest, built largely from fiberglass reinforced plastic and foam, powered by two small jet engines producing under 500 pounds of thrust each. No fly-by-wire, no computer augmentation. Just a test pilot and a rotating wing. Across 79 flights, the wing pivoted gradually from 0 degrees to 60 degrees. At small angles, the Dun behaved almost normally. Any skilled pilot could manage it. Above 45 degrees, new phenomena emerged. Cross-coupling, pitching the nose up caused unintended roll. Rolling induced pitching. At 60 degrees, pilots had to maintain constant corrective input spanking and yawing right to maintain straight flight. It was demanding, but not catastrophic, and crucially, the data showed these issues could likely be mitigated with stronger wing structures and computerized flight control systems. The Dun never exceeded 320 kilometers per hour. Its purpose, weight, and speed, it was proof to explore supersonic potential. NASA partnered with the U. Navy in 1984, the plan, modify and Fate Crusader into the first supersonic oblique test. The Fate's high-mounted wing made it a suitable candidate. NASA had already used the Crusader to pioneer fly-by-wire control systems. $36 million were allocated. Design completion, 1,986. Construction, 1,990. First flight, May 1991. It would have been the ultimate terrestrial transonic and supersonic data from a full-scale oblique wing fighter. Then funding vanished. By 1986, the Navy faced deep budget pressures. Cost overruns elsewhere consumed experimental funds. The Navy withdrew. NASA could not carry the program alone. In 1987, the supersonic oblique test was canceled. After nearly 50 years of research, momentum evaporated. Robert Jones did not stop. Into his 80s, he pursued an even more ambitious concept, a pure oblique flying wing. No fuselage in the conventional sense, just a single sweeping surface capable of Mach 1. 5 crews with economics approaching subsonic transports. Study after study suggested the concept remained viable. NASA's own assessments acknowledged its promise for large transports, but real-world supersonic validation never came. Meanwhile, commercial aviation remained conservative. Airliners today still resemble those of the 1960s incremental improvements layered atop proven geometry. Billions are spent chasing single-digit efficiency gains rather than risking radical reinvention. Modern fly-by-wire systems and advanced materials could likely tame the cross-coupling issues that challenge the Dun. Yet the oblique wing waits, symmetry still rules the sky. Robert Jones passed away in 1999, leaving behind some of the most profound aerodynamic insights of the 20th century. His work suggests something uncomfortable. We may not have reached the limits of speed or efficiency. We may simply be clinging to a familiar shape. If this challenges how you see aviation, consider this. Would you board an aircraft with a single rotating wing sweeping diagonally across the sky? Or is symmetry too deeply wired into our sense of safety? Because sometimes the greatest barrier isn't physics. It's perception.